What's cracking, guys? In this video, I'm continuing with the coding video series, and I'm not going to cover a research paper like code in this one. I'm going to cover open source ML tools and libraries, and hopefully this will help you improve your own projects by including these awesome open source libraries and tools. So in this one, I'm going to cover Jina AI, and as you can see here, they are a cloud-native neural search framework for any kind of data. So this enables you to import lightweight Google into your project, whereas the neural part means you'll be using deep neural networks to perform the search. And the any kind of data means basically you can take whatever modality you wish, so like image or text or audio or video or mesh or whatnot, and you can use those to query and find like data from any other modality. So you can use images to query for certain text snippets, you can use text to query for images or videos, or audio for mesh or whatever, like whatever combination in that combinatorial space you can imagine, Jina AI can kind of help you do that. As you can see, the README is pretty nicely structured. They have lots of resources here, tutorials. They have like lots of contributors. People are using this already. It's an established tool, as you can see here, used by 130 organizations and people already. And so the way I'd suggest you go ahead and explore this tool is by understanding these quick demos. And in this video, I'm gonna walk you through step by step through the fashion image search. Aside from that, you should probably go and understand the basic concepts of Jina. So that's document, executor, and flow. And they have really nice pages where they explain how you can use the document, how you can use all of these native concepts to Jina. So document is an abstraction they use to describe whatever data type you have. So basically, document can be an image, document can be a text, document can be video, or whatever data type you have. Don't get confused by the terminology. So document, if you're like me, a document is gonna associate you to text data, textual data only, and even the emoji here is associating us to text, but it's not. It's an abstraction object which wraps up any kind of data. Then they have executors which process the data, and flows finally organize those executors into these kinds of pipelines, as you can see here on the image. A short note on the installation procedure: because they are cloud-native neural search engine, that basically means because cloud is mostly Linux, that means they support Jina for Linux pretty much. And because I'm on Windows, this thing does not work on Windows, and I had to install a Windows subsystem for Linux. I had some problems getting it to work, but after I've upgraded to WSL2 and fixed some other small problems, like I had problems plotting because Matplotlib would not display the actual chart, so I had to do some tweaks. So if you want to know all of those details, if you're on Windows like me and you want to try this thing a go, do join the Discord community, because I'm gonna paste the step-by-step how I kind of solved all of the problems I encountered on Windows and how I got it to work. So having said that, let's start with the fashion image search. So they have a nice page here explaining how you can actually get it running, and the end result will be this. You can see here, basically we have a query image on the left, and we can fetch, they are fetching 50 closest images from the data set, where closeness is defined, as you can see here, like visual similarity in the case of images. So yeah, let's get this project started. Okay, so the first thing you obviously need to do here is do git clone the repository on your own machine, install the conda environment, and just do pip install Jina, and that's going to install Jina AI package to your environment, and then you can get started. So as you can see here, I'm on Windows, so I'm in this WSL terminal. I'm using Ubuntu as my distribution of choice. I'm just going to start Visual Studio Code. You can use whatever editor you prefer. Just kind of navigate to the root directory of your project. And again, from your environment where you're using Conda or something else, just start your IDE, and then we can get started. The first thing we'll want to do is to clone the demo example to the root directory. So I'm just going to type Jina hello fork fashion into Jina fashion demo directory. So basically this means, hey, I want to use Jina and I want to use these quick examples. I want to fork it to my local machine. I want to use fashion example in particular, and I'm going to fork it into Jina fashion demo. So if I run that, as you can see here, I just got this new folder downloaded, and I'm gonna open up the app.py. So this is the main main file, and the thing we're going to do, so we basically don't need any additional arguments, so we can just start this thing and that's it. So I'm gonna run F5 and start this project. Okay, there are some basic parameters we are setting up here. Let me quickly just walk you through them. So basically, you can see here, what is important is this part here. So what they include, they have this working directory. The work directory is just going to create a random directory inside of your root directory. And that's pretty much the only thing we care about in this one. And then what they do is they, as you can see here, they have the data URL, the labels like for the training set. So these two are for the training set. So we are downloading fashion MNIST here. And then they have the query data. So basically let's call these are test sets. Again, fashion MNIST, and we have the data and we have the labels here. So number queries is just the number of queries that we're gonna display on the web page. We'll soon see. And finally, top K means how many similar items are we trying to find for each of these queries. So those are all of the parameters you should care about. And now let's return to the app.py. So let's kind of step into this function and see what's going on. So first things first, they are going to create this random directory. So that's it. And then they're going to form this basically dictionary where they have, as you can see here, so the URL for the data and the local file name where this data is going to be saved. So we're going to save the training data directly inside of this random directory, and we're going to name this index labels file. So nothing special here. We're going to do that for both the training set and the test set, and that's it. Okay, let's continue. So next step is downloading the data. So let's step into this download data function. So basically, nothing smart here. Everything is handled by this URL lib package. So what happens is we're gonna skip this because it's none. So we're gonna install this opener, whatever. So this is just like boilerplate, pretty much. You don't need to understand all of these details. With progress bar, just a context manager to show the progress while the thing is being downloaded. And now we're going to iterate through the dictionary and download the data and the labels for the training set and for the test set. That's it. So if it doesn't exist, and it doesn't exist because we just created this random folder, we're going to retrieve it here. We're going to download it. So until this point, we just downloaded the data into those files. And now we're going to actually load the data from the files. Let's see. Load labels, let's step into that one, and it's fairly simple. What they do is they just open up that like local file, and let me show you where it is. So basically, this is the random directory I was mentioning, so it's directly inside of Jina root. You open it up and you can see index labels, so that's the first file. So now here, we're gonna open it up, as you can see here, and we're gonna load it from using NumPy and just reading the file here. So nothing you need to care about. So this is some specific knowledge because they know the structure of this file. They know that they have to offset reading 8 bytes from the very start, and that's it. Then they do the reshape part, and this is always useful to have shapes in your mind constantly when you're debugging machine learning code. So this should be 60K, 1 should be the shape of this object, because those are labels, and we have 60K examples inside of the index dataset. So I'm going to step over here, and we can check the data to see whether we are correct here. So V, I'm going to find the data array, and you can see here shape is 60K, 1. So that's it. Now we're going to do the same thing for the next label. So this is going to download the labels for the query dataset. Same procedure, so I won't be walking you through the same function again. And finally, we're downloading the actual images. After that's done, you can see in the directory we have this index original. So that means that these are actually the images. Okay, and now we're going to step into this load MNIST. I'm going to step into it, and you can see again we just open up the file, we read it. We have this NumPy from buffer, and we reshape it into 60K 28 by 28 because we have MNIST images here. So that's it. It's fairly simple. I'm going to just step over this, and we're going to see that after I do this. So we data and we have 60K 2828. Those are obviously MNIST images. And finally, last step, we're gonna do the same thing. So we're doing the same thing just for the query dataset this time. And I'm gonna step over this time. So we're gonna load the data, and that's it. We downloaded the data, we loaded the labels, we loaded the like images, and that's it. So that data is currently stored into this dictionary. So we have targets. You can pick whatever type of data you want. So for example, we can pick index labels. So that means the index data set, the labels, and you'll find the data array here. So it's 60K1. You can do the same thing for example, index, which is images, and you can see the data 60K 2828. So everything is stored into this, neatly stored into this dictionary object, and that's it. Now this is nothing that important, just some optimization stuff. And finally, this is the flow object I mentioned in the initial part of the video, which is one of the building blocks of these Jina like programs. And what flow does is just organizes these executors into this nice pipeline, which you can then run and execute, process the data in whatever manner you wish. So as you can see here, we're gonna form flow, and we're gonna add these. So these are called executors. So we have executor that's called MyEncoder. We're gonna see what that thing does in a couple of minutes. We'll have two of those in parallel. Then we'll have the indexer, and the indexer is going to index this thing into this work directory, which is the random UUID directory, as you can see here, the string on the screen. And finally, we have this MyEvaluator executor, which is going to do some the actual searching and matching of the image embedding vector of the query embedding vector to the all of the other index embedding vectors. So that's it. And now, because this is lazy execution, this object still, the constructors of these executors are still not called. That's going to happen after we open it up with the context manager here. So only here will they actually execute and form those executors. So that's the lazy execution design pattern. So the thing I'm going to do now is actually visualize this flow. So I'm going to stop this program. I'm going to add the plotting function here, so we can plot. You can actually plot these like flows. And I'm going to just save it into TamFlow SVG, and that's it. I'm going to save this. I'm going to rerun it, and I'm going to show you what happens. So we're here. If I do a step over, let's do a step over. It's going to form this SVG, and I'm going to open it up and show you how this thing looks like. Here it is. It's you can see the temporary flow SVG file in the root directory, and for some reason it's going to open it up in Microsoft Edge, even though my default browser is Google Chrome. So let's open it up here, and you can see the actual diagram. So we have the input here. We split the input into two MyEncoder executors. Then we have the MyIndexer, and then we have the MyEvaluator. If we were to put some names as the arguments to those here, basically name, they have a name parameter, blah, blah, blah. We have nicer diagrams, but you get the point. Okay, having done that, let me now show you what I meant by the lazy execution. So we're here now. I still haven't executed this line. So if I go to, let me find the files. Let me find the actual my executors folder. So I'm gonna put some breakpoint inside of the constructors here. So init functions, MyIndexer. I'm gonna put a breaking point here, MyEncoder, and finally I'm gonna put a breaking point into MyEvaluator. And so now I'm gonna put a breakpoint here. And I'm going to step over this line here, and we're going to see it's going to hit the constructors of those executors. So F10, and you can see here MyEncoder is hit here. So I'm going to do F5 again. We hit encoder again because we have, as you remember, two encoder executors in parallel. So I'm going to step over F10. So F5 indexer and F5 evaluator, and that's it. F5 will bring us to the next line, F index. Okay. So you saw that by doing this, we only then executed the constructors of all of the executors you've inputted here. And now we're gonna hit the index function. So first, let me break this down on a high level for you, and then we're gonna step over the code. So we have, as you can see here, the main function. There is not much lines of code here left. It's fairly simple. We have we're calling flow index, which is the same thing as if we were to call this post function. And instead of using /eval here, we'd be using /index. So these are the same things. So the indexing function is gonna, as you can imagine, index the data and gonna create the embedding vectors. And then the eval function is gonna do the actual matching. So once we call the eval function, we're gonna actually find the 50 closest matches to that query image, okay? So that's like the rough pipeline. And then finally, after we have the data, we're gonna write it into HTML, and we're gonna be able to open up this HTML page in the browser and see the final results. Let's go a bit deeper, and then I'm gonna step into this code. So next thing you see, we have these generators. We have index generator here, we have query generator here, and we have some additional parameters, not that important. Show progress is just gonna show us in the bar as this thing is being indexed and evaluated. We're gonna see the progress in the console. Print results. So once this thing is done, the print result is a callback function, and it's just going to dump all of the result into some data structure, which is then going to be used by this write HTML function. So that's the whole point there. Top K is just the argument, so it's currently 50, which means we're gonna search for 50 closest matches inside of the index data set using the query vector. And that's pretty much it on a high level. Before I show you how these post functions work, let's step into the generator itself and see what's going on there. So the generator is gonna iterate over all of the 60K docs, as you can see here, and it's gonna basically load. You can see here the structure of the dictionary. We fetch the index data, and then we just fetch the first image. And for some reason, they are inverting the image with 255 here. I'm not sure why this is. If somebody knows, feel free to comment down below. But for some reason they are inverting it. And now what the next thing they're gonna do is, because this is just a grayscale image, they're gonna do stack times 3 here, which is gonna form RGB image. So they're basically gonna copy that channel 3 times and get an RGB image. So now this is the document. So this is the third core component of Jina framework. So I mentioned flow, I mentioned executors. So document is just like a wrapper object around all of different data types. So here we're gonna form an image, and so I'm gonna step over here, and we're gonna set a tag ID to this. This is going to be 0 because we are iterating, remember, over all of the 60K docs. So that's it. Now we're going to yield D, which basically this is the generator syntax of Python. I'm not gonna dig into that a lot deeper, but yeah. So if I step over again, it's gonna hit the same line again, and you may wonder why is that. So the thing is, the way this is set up in the background is this generator is gonna yield 100 images, and only then will the post function we just saw, so from the flow object, is going to execute. While this thing is generating images, let's return back to AppPy. So it's going to generate 100 images, and the reason is, as I already explained, there is a hidden default argument that's 100, and after it's generated 100 images, it's going to call, the index is going to trigger. And what happens once index is called is all of the executors, which have these request methods defined, all of these functions which are decorated with this at requests on index, are going to get called, and not only those functions, but also the functions that don't have any on parameter here. So we're going to see what I mean by that. So requests, so I'm going to put a breakpoint here. Requests, we have, this one is triggered on search and eval, so we don't have to worry about it yet. So this one is, as you can see, that doesn't have the on part. So that means every single flow post function is going to trigger this one. So I have a breakpoint here. And let's go further on. This converter function is not called, so I'm going to skip it. And this last one is eval, so it's not going to be called as well. So the functions that are going to get called right now are the basically encode function and the index function. So let's kind of step over here. So I'm gonna hit F5. That's gonna generate 100 images, and the index function will be called. So F5, and as you can see here, the encode function is the first one to be called. Let's understand what's going on here. So docs is just an array of 100 images. Remember, that's the images generated by the index generator. So we're gonna fetch the content, which is going to fetch all of the images. We're gonna stack them, and we're going to end up with 100, 24, 24, 3. The shape will be something like that, I suspect. So let's see the content part. So the shape is 128, 28, 3, because remember, we have RGB MNIST images, we have 100 of them because of the generator, and that's it. Now we're gonna reshape them, so they're gonna extract only single channels. So I don't know, I'm not sure why we had to form RGB images when we were extracting single channel here, but yeah, whatever. So basically, we're reshaping these 784 because 24 squared equals that number. So we're gonna just flatten it out, and you can see here 100, 784. And now this is a funny part. So the first thing they're going to do is, because these MNIST images are in the 0 to 255 range, so they're going to normalize them to 0, 1 range, and then they're going to do this multiplication with this other matrix, and that's going to form the embedding. So let me kind of explain what this actually does. So first things first, let's see the shape. The shape will be of the, so we have self-other matrix. Let me find that one. So it's, as you can see here, 784, 64. So once we multiply, so we have, remember, we have 100, we have 784 here. So that's this matrix, and then we multiply that thing. So let me put brackets here. So we multiplied with 784, 64. That means we're gonna convert this shape into 164. So we basically embedded all of those images into this 64-dimensional embedding vector. So the logic here is not actually a neural network. The thing they do is, in the like constructor function, they just form this random matrix that has exactly this shape. Then they apply the singular value decomposition. I'm not gonna go into details here. It's an ML technique. The thing you should probably know is that any matrix, no matter the shape, so it doesn't have to be a square matrix, can be decompositioned using SVD. So once we have SVD, the nice property of these two matrices is that they are orthogonal. That means once you multiply a vector by this matrix, the vector is just gonna change the rotation, but the length will stay the same. So it's preserving the length of the vector. So it's just rotation matrix. And what they do is they multiply these two matrices to form this other matrix. So just a fancy way of creating an orthogonal matrix, i.e. the matrix that does rotations of this particular shape, and that's going to embed all our vectors into this 64-dimensional vector. That's it. Okay, let's continue here. So let's press F10 here. So now the next thing that's going to happen is we're going to iterate. We're going to fill in these documents with embeddings. You can see here embeddings, and the content. Content is just the flattened out MNIST image. This function is going to convert the actual blob, the image, into URIs, which is unique resource identifier, which is basically like a long string that's going to be an equivalent representation of this image. And then they're going to pop the blob. That's it. We're gonna repeat this for all of the images, and that's the encoding part of the index of this index function. So remember, we have 100 images here. Now we just did is we embedded all of these images, and the next thing we're gonna do. So I'm gonna just press F5 here. We should hit one of the other functions. So the indexing function, I guess. So F5, and as you can see here, the indexing function, the only thing it does is it has this docs, like private variable, which is a document array mem map, and just another object from Jina, which helps you kind of optimize memory-wise and time-wise the performance. So I won't get into the details because it's just an optimization trick. Okay, so we're gonna just dump all of those docs, which now, remember, contain the embeddings as well as the original images, converted into URIs. I went ahead and executed the whole index function because it takes roughly 58 seconds on my machine. So yeah. So what happened is, again, we chunked the data, the 60K images, into 100 images per batch, and we did the embeddings. We did the extension of that specialized memory object. So we just kind of added all of those documents with the embedding vectors to that specialized memory object. The second thing that's going to happen is we're going to call the post eval function, and this again has this query generator. So I'm going to step into it and put a breakpoint here. So put a breakpoint there, return here. So we're going to step over and see what the query generator is doing, and then we're going to set the breakpoints to all of the executors which are kind of sign up to listen to this eval call. And I've set the breakpoints to all of those eval functions already. So let's just step over here. So query generator, you can see the number of queries, 128. We have the target, so that's the dictionary that contains all of the data, and with ground truth equals to true. Let's see what that means. So query generator. Okay, what this line will do is the following. It will find, because we have, remember, we have MNIST data set, and we have like, I think there are 10 classes inside of it. So what it's going to do is return this object, which will contain the following thing: a dictionary that will have a label, and then all of the images from the index data set that have, so all of the IDs that have label 0. and then the same thing for label 1, so IDs here, etc. So let me step over this code, so F10, and see what GTS looks like. So again, and if I expand 0, somewhere in there you can find the information of the IDs of images or the document IDs. So now a small drawback with Jina, in my opinion, is that it's kind of hard to find in these, as you can see, in variables while you're debugging the code, to find the actual information you need, because there's a lot of metadata and things you don't care about because of all of these complex document objects. But it's also a good thing, I guess, at the end, because it's wrapping up a lot of functionality for you. So now we're gonna iterate through the all of the docs. We have 128 query vectors. So we're gonna do 128 times. We're gonna form a random query vector, so random ID from this, because we have 10k query images. Remember, we're gonna form a random ID here, and we're gonna just fetch that image. That's again black and white first, and then they form RGB image, and then they just kind of wrap it up into the document. And because the ground truth is set to true, we're going to return not only the query image, but also the actual ground truth label. This is again going to be called 100 times, and only then will we have the post eval function being called. So I'm just gonna step over until we hit the first breakpoint. And here's the funny part. So basically what happens here is the docs contains 100 query images, and it's gonna do match function with this self._docs, which, if you remember, contains the index images with all of the embedding vectors. So what we're going to do here is, for every single query image here, we're gonna find the closest image in the index images using cosine metric, just doing some normalization to 0 from 0 to 1, and finally we're gonna fetch top k, which means 50 closest images using the cosine metric. So in the background we're gonna have like a for loop, simple like comparisons, and at the end this docs container is gonna contain all of the matches inside of it. I'm gonna again step over and get to the next breakpoint. Finally, we are here in the last executor. So this here we're gonna calculate the precision and recall metrics. So we've done the matching. We now have, for each query vector, we have associated 50 images from the index data set or from the trained data set. And let's see some information here. So I can use VS Code's nice functionality here and plot the number of documents we have. So that's 28, and it's 28 because we have 128, remember, and we're chunking into pieces of 100. And so 128 modulo 100 is going to give us 28 query vectors in this iteration. So ground truths again contains the basically the IDs of those images in the index data set that have the same label as a particular query vector. So let me kind of break that down. So let me step over here. So first things first, so this is a query vector, and these are the matches from the last function. So basically these are the 50 images, and we're gonna grab their IDs. So we're gonna grab the IDs of those images from the index data set. So let's see that. So if I print actual here, actual. Okay, so we can see some numbers. So those are the IDs of the images from the index data set. Now, these are floats. Obviously, there are some small inefficiencies and problems with this example, but it's working functionally, it's working correctly. So, and finally, desired contains the, basically, as I said, all of the IDs that have the same label as this query vector. So that means because we have 60k images and we have 10 labels, I can expect to have 6,000 IDs here. So if I kind of print length of desired like this. Oh yeah, I have to step over it. So if I now try and print this, it's 6,000. So yeah, and now we can kind of do the intersection between the actual IDs we got and the desired, so the ones that have the same label as the query vector, and we can find the precision and recall metrics. I'm going to skip over that. It's a simple logic, and that's it. Now I'm going to basically remove this breakpoint and jump to the final step of this whole program, and that's writing all of this data into an HTML document and kind of rendering it inside of a browser. Okay, here we are. As I said, we had this post eval function being called, and at the end we had this callback function. So let me kind of quickly walk you through what happened there. So after we finished the calculation of precision and recall metrics for every single query vector, now this function kind of populates this is a simple Python list. It populates it with HTML syntax. So we have, as you see here table row, table cell, and we paste the like original query image, and then we iterate over all of the matches. So over the 50 matches, we add all of those matches in the same row, and then we close the cell, we close the row, and we repeat that for every single query vector. That's 128 query vectors, and that's how this thing is formed. And after that, let me kind of like jump into write HTML function. I'm gonna put a breakpoint here and gonna press F5. So here we are. It's gonna open up this demo HTML, which is a template like a HTML file, and it's gonna replace some of the placeholder variables. Like as you can see here, result. We're gonna put this result HTML, so that's the same, just this Python string we just created that contains the content of the HTML file. So yeah, we're gonna replace all of these templates, placeholders, and finally we're gonna get, let me jump to this web browser open. It's gonna fail because I'm in WSL, but that's just on my system. It's gonna work for you much better. And I'll just manually open it up. So that's it. I'm gonna press F5. This is the end of the program, and I'm gonna open up the HTML. Okay, here is the HTML. Let me open it up, and here are the results. And as you can see, on the left-hand side, we've got query vectors. On the right-hand side, we have the matches, so the 50 matches for every single query vector, and there is 128 of them. And as you can see, our results look pretty decent. Like if we focus on one particular image, like I don't know, like this shoe here, we can see that most of these results are shoes. They're not, even though there are many other images in this data set, like bags or whatever, trousers, I don't know. There must be some like failure cases, but I didn't manage to see anyone. I don't see any failure case here in particular, but yeah, hopefully you got some idea what Jina can do. And let me just kind of mention that this second example with the QA, the question answer, like chatbot, is maybe a bit better because remember that Jina is a cloud native neural search, so cloud. And this example here, what it does is it's very similar, but like it opens up a chatbot, so it creates a Python server. And so what happens is there is a communication happening between a Jina Python server and this JavaScript code in the browser. And so you basically input like a query, like a text query inside of the browser. It gets embedded. The Jina does its magic of finding the similar, the most similar match. So the most similar response, the textual response, and it communicates it back via the this HTTPS, I guess, like a link to the JavaScript code, and it just renders the response. So it's a very similar example, but it basically paints a clear picture that Jina is used for these cloud types of applications, and because here we have explicitly like a Python server. So hopefully you found this video useful. If you did, share it out with a friend, subscribe to the channel, hit that bell icon. Also, if you have any feedback on this video or what you would like me, which ML tool you'd like me to cover next, let me know down in the comments, and also join the Discord community. Until next time, bye bye.